Hello everyone. Today I'm going to show how to do the sorting using the QuickSort algorithm. So QuickSort algorithm is also called divide and conquer algorithm because we are dividing the array and then we are sorting. So it's also called divide and conquer. So let's see. Okay, so it's divide and conquer. Okay, so let's take an example. Okay, suppose I have an array 10, 80, 30, 90, 40, 50, and 70. Okay, now I want to sort this array. Now in order to sort this array using quicksort, the first thing that what I'm going to do is I am going to partition this array in such a way that I have all less than element. Okay, so I'm going to choose one pivot element. So for example, if I'm choosing 70, okay, the last element as my pivot element, then I have all elements less than 70, less than or equal to 70 will be on the left side of 70, and all elements that are greater than 70 will be on the right side. So this is the first step. So this is called the partition step. So we are going to partition the array such that all element less than equal to 70 will be on the left side and greater than equal to 70 will be on the right side. Okay, so once I do this partition, my partition function will return me the index of this pivot element. Okay, so it will return me the index of the pivot element. So now 70 is at the right position in the array. Then what I'm going to do is I'm going to call the same quicksort algorithm on the left side of the array, and I'm going to call the same quicksort algorithm on the right side. So I'll call this quicksort on the left side, and I'm going to call the quicksort for the elements which are on the right side because we know 70, the element 70 is at the right index, so we need to sort the remaining array. So this will sort the left half and this will sort the right half. Again, here we'll choose one pivot and all the element to the left of the pivot will be on the less than equal. All the elements which are less than equal to pivot will be on the left side, and all the elements greater than pivot will be on the right side. So we keep doing this until the array is sorted. Okay, so let's trace through this. So the main important function, the all work is done in this function, the partition function. Okay, so let's see how we're going to do this partition. Okay, so let me continue with the same example and let's see how we're going to do that. So first thing, so now this is my partition function. Okay, my partition function or a method. I'm going to pass this array, my array A, and then I'm going to pass the index, the low index, and the high index. So for my this array A, the low index is 0 and high index is 0, 1, 2, 3, 4, 5, 6, 6. So that's 6. Okay. So this is my partition function. So what I'm going to do is I'm going to choose the last element, okay, as my pivot element. So my pivot element is 70, okay. I know my pivot is 70. Now, so I'm going to choose one index, okay? This index will be -1, or you can also tell it as low -1, okay? So this index, okay? Now remember this index, all the elements to the left of this index will be less than, including this element itself will be less than equal to pivot, and all the element to the right side of this index will be greater than pivot. So that's our index I. Now I'm gonna scan this array from left to right, okay? So my j is equal to 0. I'll take the first element of the array, which is 10, okay? So 10, 80, oh, I'm sorry. So we have 10, we have 80, we have 30, 90, 40, 50, and 70, okay? So now we know this is my first element. J is 0, so this is my element. I'm going to compare this element with this pivot. Okay, so 10 is less than equal to pivot. So I'm going to swap. Okay, I know this is my index. Okay, this is my less than equal to index. So all the element to the left of this index should be less than equal to pivot, and right should be greater. So what I'm going to do is I'm going to swap this element with this. Okay, so I'm going to increment I, so I will also be the same element, which is 10, and I'm going to swap 10 with itself. So in the first iteration it will do nothing. So let's go with the next iteration. Okay, so we are scanning from left to right. Okay, so now my j is incremented, so my j is this 80. Okay, and my I is this. Okay, now I know all the element to the left of the I is, including I itself, is less than equal to pivot. Now my j is 80. Okay, j is equal to 1, so my j is 80. So is 80 less than equal to pivot? No. So we're gonna do nothing, and we're gonna increment j. Now j points to 30, so now my j is 2. Okay, now this is less than 30 is less than equal to 70. So I know where to place this 30. I need to place this 30 here. Okay, so because I know I is the index of less than equal to element. So all the element left of I, including I itself at that index, should be less than equal to this pivot. So what I'm gonna do is I'm gonna so what I'm going to do is my I is 1. So I'm going to increment my I. So my I will become 2. I is equal to 2. And I'm going to swap this 30. Okay, I'm going to swap this 30 with this one. So the array that I'll be having is this. I'm swapping 30 with 80. So 30, then 80, 90, 40, 50, and 70. So my I is here. Okay, all this element, okay, this are less than equal to pivot. My j is here, so I'm going to increment my j, so my j will be here. Okay, so now this thing, right, 90 is less than equal to 70? No, so I'm going to increment my j. So let's increment j. Okay, so now j is here, so j is here. 40 is less than equal to 70? Yes, it is. So what I'm going to do is I need to place this 40 here, right? Here. So what I'm going to do is I'm going to increment I, and I'm going to swap 40 with this 80, okay? So let's do that. So now, so 10, 30, I'm going to swap this 80 and 40. So now I'll have 40. I have incremented my I, okay, and I have swapped this I and j. Then 90, I have swapped 80, so 80 will come here. 50 and then 70. So I'm going to increment j, and now j will be here. 50 is less than equal to 70. Yes, of course. So I need to move this 50 here. Okay. So I'm going to increment I, and then I'm going to swap 50 and 90. So that will give me 10, 30, 40, 50, 80, 90, and 70. Now my j is here and my I is here. Okay. We, we so we have chosen this as a pivot. So we're gonna scan left to right till this n minus 1. So we're gonna scan from 0 to fifth element. So now we are done with this j loop. Okay, so we are done with the j. J is here and we are done. So now we have all this element. All this element, they are less than equal to pivot, and all this element are greater than equal to pivot. So we're gonna come out of this for loop and we're gonna do one last swap where we are going to increment I, and we're going to place 70 in between here. So we're going to place 70 here. All these elements are less than equal to 70, and on the right side the elements are greater than 70. So let's do that. So let's increment. So we're going to swap it. So we're going to increment I. So now I will be here, and we're going to swap this pivot and this I, the high element, okay, the pivot and the high. So it will be 10, 30, 40, 50, 70, 90, and 80. Okay, so we have swapped this array of high with array of I. We have incremented I and we have swapped this too. Okay, so now this is our array after partitioning. Okay, and what this function will return? This function is going to return this, the index of this pivot element. So the index is 0, 1, 2, 3, 4, 4. So this function will return 4. Okay. Once this function return 4, what we are going to do is we are going to recursively call QuickSort. So we're going to call QuickSort with the left and right. Okay. So the QuickSort will have our array, will have low, and whatever the index of pivot -1, because we know this pivot is at the right position, and we're going to call the quicksort function again. We'll have our array, then we'll have our pivot +1 and high. So we need to call quicksort on this left side and right side, because this is at its right position. Okay, the pivot element is at the right position. So now let's look at the code, then we're going to look at the time complexity. Okay, so now let's look at the coding for the quicksort. Okay, so as I told you, right? So we have two methods, the partition and the quicksort. Okay, so we have this method. So we have quicksort, and we're going to pass our array, which is an integer array, and then this array has low and the high index of the array. And here, so now if low is less than high, right? So for example, if the array is empty, right? If low is less than high, then we're gonna do nothing. Sorry, if low is less than high, then we're gonna do whatever we need to perform as long as the low is less than high. But if we have only one element, right? If we have only one element in the array, then low will be equal to high, and in that case, we don't need to sort our array. So if low is less than high, then we are going to sort our array. So the first thing, okay, the first thing that we're gonna do is we're gonna get the pivot position. And for that, what we are going to do is we are going to write the partition method, which is going to which will take our array low index and the high index. And this method is going to return the position of the pivot, which is a pivot index. So it's going to return pivot index. Once we get the pivot index, we know that the pivot element is at its right position in the array. So what we need to do is we need to recursively sort the left of the pivot and the right of the pivot. So we are going to recursively sort the left half of pivot using the same, we'll recursively call our QuickSort algorithm, which will again take our array. The low index is low, and we are going to do the we are going to recursively call quicksort on the left half of the left of the pivot. So it will be pivot index minus one, and then we are going to recursively sort the right half of the pivot. So recursively sort the right half of pivot. So we are going to call again our quicksort algorithm. It will take our array. Now here we are going to sort the right half of the algorithm. So it will be pivot index plus 1 and whatever our high index is. And this is our main quicksort function method. So now we are going to write the partition method. Okay. So what does first, let's understand what does this partition method does. Okay. So it is going to place the pivot element at its right position, and it's gonna return its index. Okay. So all the smaller elements, right? All the elements which are less than equal to pivot are placed to left of pivot, and all the greater elements are placed to its right. Okay. So let's do that. Okay. So let's write that method. So this method is going to return integer, which is the pivot index. Okay. It's gonna take integer array, integer low, integer high. So now what we are going to do is we are going to choose our pivot. Okay. Now in this case, we are going to choose the last element as our pivot element. Okay. Now we can choose any random pivot also, but in choosing the random pivot, that's too much. It's overkill. Or you can choose the median of 3 to 5 values as a pivot. So we are going to choose array of high as our pivot element. And now we are going to place this pivot at its right position. Okay. Then we have this index, which is less than equal to index. Now this index all the elements to the left, including this index, is less than equal to pivot, and all the elements to the right will be greater than pivot. So this index will be low minus 1, or you can just define it as minus 1 also. Okay. And then now we're going to loop through all the elements of the array from left to right. Okay. So for integer j is equal to low, our last element is the pivot element. Okay, so we are going to loop from 0 to n minus 2. Okay, so j is equal to low, j less than high. Okay, so if high is 6, if we have element from 0 to 6, we're gonna loop from 0 to 5. So j is less than high, j plus plus, and then um, so what we are going to do is we are going to compare this jth element with the uh, with the with the pivot. Okay, so if jth element is smaller than pivot, what we're going to do, we're going to increment I, which is our less than equal to index, and we are going to swap which two elements, we are going to swap jth and ith element. Okay, so if, okay, we're going to compare the jth element with the pivot. So if array of j, okay, is less than equal to the pivot element, what we are going to do, we are going to increment our less than equal to pointer. So we're going to increment I, and then we're going to swap the ith element and the jth element. So we're going to swap I and j element. Okay, so we're going to swap. So this will place all the less than equal to element to the left of the pivot, right? Greater than equal, greater element to the right of the pivot. So we are swapping the element, all the less than equal to element. Okay, we are incrementing the ith index if we are going to do the swap. Okay, so if we have jth element less than equal to pivot, then we're going to grab that element and we're going to place it at I plus 1 index. If the element is greater, we do nothing, we just increment the loop. So here, once we are done scanning all the element from left to right, right? So you will have all less than equal to element, all the element at index I, right? Less than equal to index, which is ith index. All the element to the left of it, including that index, will have all the elements less than equal to pivot. Okay. So now we need to place the pivot in between. So we are going to increment I again, and we are going to perform one more swap so that the pivot is at its right position. So we are going to swap I, and we are going to swap the pivot element, which is at index high. Okay, so now this will place pivot at its correct position. Okay, and what we need to return, we need to return the pivot index. Okay, so we are going to return I, because the pivot is at index I after this step. Okay, and we also need to write our swap method, which is just swapping the two elements of the array. So swap method will take integer array, integer I, and integer j, the two index that we are going to swap. So integer temp is equal to array of I, array of I is equal to array of j, and then array of j is equal to temp. Okay, so now we are done with our swap method also. So this is the complete quicksort algorithm. Now let's look at its time complexity. Okay, what is the time complexity of this algorithm. Now to understand the time complexity of this algorithm, let's look at the algorithm tracing that we did. Okay, so uh, let's look at that. So we are going to look at the tracing. Okay, so let's look at this. Okay, now, okay, so we have these elements. Okay, we have 3, 6, 5, 4, 2, 1, and -1. Okay, so what will be the first step? We're going to choose our pivot, right? Our pivot will be, let's say, for example, we are choosing the lowest element as our pivot. So we are choosing 3 as the pivot, right? So the first step would be we are going to perform that partition on all of this element, and we're going to place all the element which are less than equal to 3 on the left and all the elements greater than equal to 3 on the right. Sorry, greater than 3 on the right. So the element which are less than equal to 3 are 1, -1, and 2. So that will be placed on the left of the 3, and the element greater than 3 will be placed on the right. Right? So after the first iteration, right, of the partition, we'll have this. Okay. Then now we're gonna call this quick sort again on this left array and the right array. Okay, so once we do this, okay, so here again we're gonna choose our pivot, which is 1, and the element to the left of the 1 will be -1, right? 1 is our pivot, and the element to the right of the 1 will be 2, right? And again we're gonna do the same thing for this array. So here our pivot is 5. So the left of 5 will have 4 and the right of 5 will have 6, right? And then we have only one element left. Okay, so now we're not gonna go in that recursive algorithm. So here we have low is equal to high, so now we're not gonna go inside. So if you look at this, right, so this is a tree structure. Okay, so we are recursively calling this. Okay, so this is like a tree structure. So this is level 1, this is level 2. Okay, so what work we are doing here? So for this first, right, we are scanning all the n elements, right? Uh, so um, so let's do this. So here, right, for at this level, we are scanning n minus 1 element. At this level, how many elements we are scanning? So at this level, we are scanning n. So at each level, right, at this level, so the amount of work, what is the amount of work at each level, right? That's what we need to find, right? So here we are scanning, uh, here we are scanning n, so it's half, right? So here we are scanning n by 2 elements, right? And here we are scanning n by 2 elements, right? And at this level, at the first level, we are scanning all the elements from left to right. So the work that we are doing at this level is n. And the work at the last level that we are doing, we are scanning n by 4 element. Here we are scanning n by 4 element. And here also we are scanning n by 4 element. And the same work we are doing here, n by 4 and n by 4. So remember our algorithm. At the first level, we are scanning all the elements from left to right till here, right? So n minus 1, which is equal to n. Here we are scanning all of this elements, right? Which is n by 2, right? So if n is around 6, if n is 6, then this is 3 elements here and 3 elements here. So this is n by 2. So we are doing this work, right? So we are doing n plus n by 2 plus n by 2 is nothing but n, right? So at level 1 we are doing n work. At level 2 we are doing n by 2 plus n by 2, which is equal to n. At level 3 we are doing n by 4 plus n by 4 plus n by 4 plus n by 4, which is equal to n. So at each level, right, at each level, the work done is equal to O of n, right? And how many levels we have? So this is a tree structure, okay? So this is, if you look at this, right? This is a tree structure, right? This is a tree structure. So what is the height of the tree? The height of the tree is always log of n. So if we have 8 elements, then log of 8. Log of 8 is log of 2 raised to 3, which is equal to 3. So we have the height of the tree will be equal to 3. So we'll have 3 levels total. 3 levels, right? So the height of tree is equal to log n, and at each level we are doing n work, okay? So the total time complexity is equal to n times log n. So it's bigger of n log n. So that's the total time complexity. What is a space complexity? So here we are not using any extra additional space, but we are making a recursive call, right, to this quicksort function method again and again. Okay, so whenever you make a recursive call, it creates a tree, it creates a stack in the memory of those calls, right? So there will be a stack space complexity, the stack space complexity, which is nothing but it will be the height of the tree, which is log n. So there is no additional space complexity, but there is a stack space complexity, which is log n, which you can ignore it in case of sorting algorithm. So this time complexity, right? You get this time complexity is in the best and average case. Okay, now what is the worst case? Let's look at the worst case of the quicksort algorithm. So think of it that you have a quicksort algorithm, and that is already you need to perform a quicksort on an array that is already sorted. What would be the time complexity of that algorithm? So let's look at that. Okay, so now let's look at the quicksort algorithm. Um, Running a quicksort on a sorted array. So I already explained, right? So if you have this array, which is not sorted, right? 3, 6, 5, 4, 2, 1, and -1, and you are choosing this as a pivot. So after doing partition, right, you will have all the element to the left of this pivot, which is less than equal to pivot. So you'll have 1, -1, and 2, and right you'll have greater element, so you will have um, 5, 6, and 4, right? And then you are choosing this as the pivot, so you'll have left, again left, and you'll have right, and then you are choosing this as the pivot, so 5, 4, and 6, right? So you already know, so this is a tree structure, and what is the height of the tree? Log n. And what is the work you are doing? Here you are doing n work, here you are doing n by 2 work, n by 2 work, n by 4 work, n by 4 work, n by 4, n by 4. So at each level you are doing n work. So this is the time complexity, which is the best and the average case scenario. Now let's see if you have a worst case scenario in which the given array is already sorted. Okay, so in that case the time complexity will not be n log n. Okay, so you have this array. Okay, 6, 5, 4, 3, 2, 1, -1, right? This array is already sorted, right, in the decreasing order. So you are choosing this as a pivot, right? So I have chosen 6 as the pivot. I don't have any element greater than 6, right? and all the less element will go here. Okay, so we'll have 5, 4, 3, 2, 1, and -1, right? So here I scan how many element? N element. Here I'm scanning n-1 element. And then again, I'm choosing this as the pivot, which is 5. And again, I'll have 4, 3, 2, 1, -1. I'm going to choose 4 because here I'll have nothing. It will be the empty array. Here I'll have nothing. It will be the empty array. Here I'll have nothing but the empty array. And here again, I'll have 3, 2, 1, -1. And then again, I'll have 3, then I'll have 2, 1, and -1. So what is the height of this tree? The height of this tree is not log n, but it is n. So the height of the tree is n, and we are doing n work at each level. So the complexity is n times n, and so the worst case complexity is bigger of n square. So that is very important. That's the worst case complexity. Now, I want to explain one more thing, which is like a stable algorithm. Okay, so what is stability? Okay, which algorithm is called a stable algorithm and which algorithm is not called a stable algorithm? Okay, so stability means you preserve the original order in case of duplicate keys. Okay, so if I have this, okay, if I have, um, let's say, if I have this order, let me take one order here. Okay, so if I have this, right, if I have 4a, okay, I'm just adding a prefix a, okay, just to identify this number, okay, 2, 3, 4b, and 1. Okay, so this is just to identify this number 4 from this number 4. So we have two duplicate number, okay. So when I perform quicksort on this, okay, so what will happen when I perform quicksort on this, right? Our pivot will be this, the last element, and all the element to the left of 1 will be less than equal to. So there is no less than equal to element. So we have our pivot and we'll have this. So what we are going to do is when you do the partition, right? When you trace from left to right, right? I will be here. Sorry, I will be here because we are not doing any swap. So I will be -1 and we'll do j all the way till here. And there's no swap that has been performed. And at the last, we're going to place this one here. And we're going to move this at one's position. So after performing the swap, what we are going to have is we'll have 1 here, then we'll have 2, then we'll have 3, then we'll have 4b, and then 4a after running partition. Then we are going to call the quicksort on this part, but so as I told, right, it's already sorted, so it will be O of n square. But we are going to call quicksort on this thing. But the thing is, look at this order. So 4a, this duplicate value came before this. But while performing the partition, right, the order is not preserved. Now we have this value 4a after 4b, right? So the quicksort is not a stable algorithm, okay? Quicksort is not a stable algorithm. Now, which algorithms are the stable algorithm then? Right, the quicksort is not. So for the insertion sort and the bubble sort, they are the stable algorithm.